These are notes for AP Calculus on the topics of differentiation and continuity. So let's first review what the definition of continuity is. A function is continuous at a point x equals c if the limit as x approaches c from the left equals the limit as x approaches c from the right. And the limit as x approaches c, the general limit, equals f of c. Look at visually what that is. So the limit as x approaches c from the left equals the limit as x approaches c from the right. But there still could be a hole right there where they meet. So the limit from the left and right, here they're both approaching the same thing, but that doesn't mean it's continuous because you could have a hole. So that's why we need this last part of the definition, which is saying that that general limit, which the left and right equal, exists because the left and right are the same, has to equal f of c, that just represents the y coordinate. And if the limit from the left to right equals the y coordinate, that means the y coordinate is going to be right there, and it's not going to be a hole. It's going to actually equal what the y coordinate, the point's going to be right there. And in order for a function to be differentiable, which means the derivative exists, it must first be continuous at that point. So it has to be continuous to be differentiable. And if a function is not continuous at a point, then it cannot be differentiable at that point. So again, it first has to be continuous for it to be differentiable, to be able to find the tangent line, to find the derivative. Okay, now let's look at some cases where the function is continuous, but not differentiable. So you can see our linear absolute value graph here. You can see at this point right here, it's continuous. They do meet up. So this graph is continuous on negative infinity to infinity. But we've got a corner right here. So we've got an abrupt change in the slope. So because of that, there's no way of knowing if this is the tangent line or it's going to be moved around. See, there's no way of knowing which of these would be the tangent line at that point because of that abrupt change in the slope. Can't tell. So it's differentiable on negative infinity to 0, parentheses, and union from 0 to infinity, everywhere but that corner at 0. In a similar case on the next one, it's the same idea, except since from the left and right, these actually approach negative infinity and infinity, this is referred to as a cusp. But it's the same reasoning. Got an abrupt change in slope for both of these. So again, if you try to draw the tangent line there, you can see there's no way of knowing exactly where that's going to be because of the cusp, because of the abrupt change in the slope. So again, it would be continuous everywhere from negative infinity to infinity. but it's not differentiable this time at x equals 3. So be differentiable from negative infinity to 3, parentheses, in union with 3 to infinity. And the last case, that's what we've got here. No corner or cusp, but if you look right here at negative 2, hard to tell exactly what that is, but right there at negative 2, we've got actually a tangent line, but it's actually a vertical tangent line. And when you have a vertical tangent, any vertical line, remember, the slope is undefined. Remember the reason why that is, because slope is the change in y over the change in x. But here the change in x is 0, so that's going to be undefined. So even though you can draw the tangent line, it's technically not differentiable there because the derivative or slope is undefined. So again, this one would be continuous everywhere, negative infinity to infinity, but differentiable everywhere but that vertical tangent line, so negative infinity to negative 2, union negative 2 to infinity. So those are the three cases where the graph is continuous but not differentiable. Okay, now let's take a look at a specific graph and trying to look for these places. It says determine the x values where the function is continuous but not differentiable. That's the first thing we're doing. And then also justify your answers. So below we've got the graph of f of x. F of x has a vertical tangent line at x equals negative 3. So right there's a vertical tangent line. You can draw it in there if that's helpful. And so that's one place we know it's not differentiable. So we can say f is continuous but not differentiable. At x equals negative 3. And then let's look at the justification. Since, well, the reason why we've got a vertical tangent line, which means the slope is undefined. So the calculus word for slope is the derivative, so it'd be since f prime of negative 3 is undefined. Now let's see if we have any other places where the function is continuous and not differentiable. You can see right here we've got a corner. So you could make this a whole other sentence, f is continuous but not differentiable at x equals 1, or you could just say and at x equals 1, we'll have our own justification. So f is continuous but not differentiable at x equals negative 3, since f prime of negative 3 is undefined, and at x equals 1, but this one's going to be a different justification since, well, when you have a corner, what you're really looking at is the slopes from the left and the right are not approaching the same value. That's what creates that corner. So you'd say since the limit as x approaches 1 from the left, but it's not of f of x, because of f of x, they actually are equal, because they do meet up there. So it'd be f prime of x, that's the slope from the left, does not equal the limit as x approaches 1 from the right of f prime of x. Okay, let's take a look at the next one. On this one, we've got a piecewise function, and these are often ones that are asked about continuity or differentiability. So it says, here's our piecewise function. Is g continuous at x equals 4? Well, at x equals 4, we can see we've got two pieces here. Here's the first piece, if x is less than 4. Here's the second piece, if x is greater than or equal to 4. So what we need to do to see if it meets up or not is see if the limits from the left and the right are equal or not. Okay. So, let's start with either side. Let's say we start with a limit as x approaches 4 on the left of g of x. We substitute in 4 there, that'd be 4 squared minus 4. So that's 16 minus 4 is 12. And now let's compare that to the limit as x approaches 4 from the right of g of x, the original function. We substitute in 4 for x in that piece. That's 5 times 4 minus 8. That's 20 minus 8 is 12. So because they're the same on the left and the right, and the y value equals that too because of the equal sign on one of them, in this case the bottom one, that tells us the answer is yes. And to explain why or why not, say since the limit as x approaches 4 from the left of g of x equals the limit as x approaches 4 from the right of g of x. But there's one more thing we have to say, and we could still have a hole there. We go back to our definition of continuity here. Those have to be equal, but there's also that general limit has to equal the y coordinate. So that's what we have to say here. Is that equals the y coordinate, which we know is g of, in this case, 4. All those are equal to 20. All right, so we know it's continuous. Now let's see if it's also differentiable. We know it meets up. Now the question is, does it meet up in a nice smooth curve or does it create a corner? So the way we figure that out is find the prime of x, the first derivative. So the derivative of the first piece is 2x minus 1 if x is less than 4. And the derivative of the second piece is 5 if x is greater than or equal to 4. So from the left, now we need to find the left and right hand slopes. Just like we saw in the previous one, it wasn't differentiable because the left and right hand derivatives were not equal. Let's see if these are equal or not. So let's find the limit as x approaches 4 from the left, now of g prime of x. So if we substitute 4 in there, 2 times 4 minus 1, that's 8 minus 1 gives you 7. And then the limit as x approaches 4 from the right, g prime of x. Well, there's nothing to substitute 4 into, it's just always 5. So those are not the same this time. So our answer would be no, because what's happening is from the left, we've got a parabola here, the slope's approaching 5. But from the right, we've got a linear one. Whoops. Sorry, the slope's approaching 7. From the right, we have a linear one, where the slope is approaching 5, something like that. So I exaggerated the difference, but notice it does create a corner there because they're not exactly the same. Even though they're kind of close, they're not exactly the same. So it's not differentiable there at x equals 4. So our answer here, because they're not the same, would be no. Since the limit as x approaches 4 from the left of g prime of x does not equal the limit as x approaches 4 from the right of g prime of x. Okay, let's look at one more example here, a little bit different. On this one, it says suppose the function f is defined by this function, and it tells you k and m are constants. We'll treat them as constants, not variables throughout the problem. And it says f is differentiable at x equals 2. What are the values of k and m? So we're trying to solve for k and m here. So let's see how we can do that. All right, well, if it's differentiable, remember it can't be differentiable unless it's first continuous. So let's put down that reasoning first. Differentiable, so f is continuous at x equals 2. Now this 2 is our breakpoint here. So that means the limits as x approaches 2 from the left and right have to be equal. So the limit as x approaches 2 from the left of f of x, in order for it to be continuous, it has to equal the limit as x approaches 2 from the right of f of x. On the left, we'll use the top piece, that's the left of 2. So remember, we're just looking for k and m, the constants we're solving for. So it'd be k times the square root of 2 plus 7 equals, from the right, we substitute 2 into the bottom piece, that applies to the right of 2. So it'd be k times 2 squared plus m times 2 plus 15. You can simplify that a little bit. That's a square root of 9, which is 3, so we have 3k equals 2 squared is 4, so 4k plus 2m plus 15. So there's one equation involving k and m. But usually when you have two equations, so two unknowns, k and m, in one equation, that's usually not enough. So we know more than just the fact that f is continuous. We also know that f is differentiable. So let's first take the derivative of each piece, f prime of x. Now remember, this x plus 7 inside the square, that's the same as x plus 7 to the 1/2 power. So k is a constant, so we don't need the product rule, so it'd just be 1/2 times k, the constant down front, and then x plus 7 subtract 1 from the exponent to the negative 1/2. And this applies for 0 is less than x, less than or equal to 2. I took off the equal to on the 0 because that's an endpoint, and function's not differentiable at endpoints in the graphs there. And then for the second piece, this k and m are constants, so derivative of kx squared would be 2kx. Derivative of mx would be m. Derivative of 15 is 0. It applies for 2 less than x, less than 6. Again, I took off the equal to on the endpoint because when a function just ends, it's not differentiable at that endpoint. Okay, so now let's take the derivative. Sorry, let's find the limits of each piece here from the left and right. So we know it's continuous. And we also know f is differentiable. It tells us that. At x equals 2. So let's take our derivatives and substitute in 2 from the left and right and find our limits. So let's write down here what we're doing. The limit x approaches 2 from the left. Now f prime of x has to equal the limit as x approaches 2 from the right of f prime of x. So 2 from the left, substitute 2 in the top piece. So notice the only thing left on the numerator would be k over 2 from the 1/2, the other 2 on the denominator. And then this is going to go on the denominator because it's a negative 1/2, so it would be the square root of 2 plus 7 equals 2 from the right, you use this bottom piece. Remember, just substituting 2 just for x, so 2k times 2 for x plus n. And then if we simplify this one, that's going to be 3, square root of 9 is 3 times 2, so 6, so k over 6 equals 4k plus n. So now we have two equations, two unknowns, k and m, so now we can solve it using substitution or elimination. And different ways you can go about it. Say we first want to wipe out the fraction on this one. We multiply the whole equation by 6. Then we'd have k equals 24k plus 6m. And now let's see if we can get all the terms kind of on the same side and use elimination here. So if I subtract 3k on this one on both sides, you get 0. Do a couple things at the same time here. So I'll subtract the 15, so you have negative 15 on this side. Subtract the 3k from 4k, so you get k plus 2m. And on this one, I'll just subtract the k over, so we get 0 equals 23k plus 6m. And then if we move this one over here, let's see, well, we're going to eliminate the k's or the m's. It's probably easier if we eliminate the m's. This is 2m, this is 6m, so if we just multiply this one by negative 3, that will make this one 45 equals negative 3k minus 6m. Then move this one over here, so we get 0 equals 23k plus 6m. Add those together, gives you 0 plus 45, 45 equals 23k minus 3k is 20k. M's eliminate. Divide by 20. And you can reduce that. Divide both by 5 gives you 9/4 equals k. Now we know k is 9/4. And then you can use any of these really to substitute in to solve for m. One place to substitute in would be right here because you don't have to multiply k by anything. So if you substitute right there, you'd have negative 15 equals k, which is 9/4 plus 2m. If you want, you can multiply the whole equation by 4. Gives you negative 60 equals 4 is eliminated there, 9 plus 8m. Subtract the 9 over. And divide by 8. So now we get m equals negative 69 over 8. And so what this tells us, if those were the constants, k and m, that we substitute in right there, that would make this one continuous. They'd meet up and be differentiable. So when they meet up, it'd be a nice smooth curve. It wouldn't create a corner or a cusp. And that concludes the notes for AP Calculus on the topic of differentiation and continuity.